Hello.
Hello.
Uh, good morning. Good morning, sir.
Morning.
Sir, आपने message. I think Vineet has answered that, ना?
Yes, he answered yes.
Yes, sir. Sorry, sir, थोड़ा late हो गया.
नहीं कोई बात नहीं. Actually, Parishad.
हाँ, sir.
12 बजे से actually there is PhD interview, so I'll be out from 12.
Yes, sir. Yes.
So maybe I'll try after that to join.
Yes, sir. Yes, sir.
It is going fine actually. It's good.
Thank you, sir. Thank you so much, sir. आप ही से सब सीखा था सर पहली बार ना. LabVIEW का तो इंस्पिरेशन आप और विनीत ही थे हमारे लिए ना. And you are still inspiration.
नहीं actually मैंने क्या मेरे का अंडर स्टूडेंट ने सीखा सब और मैं खुद नहीं किया ना इसलिए देखते थोड़ा. So he implemented that whatever student did. So how are you, Vineet?
I'm doing absolutely fine, sir. Going good. I want to visit Pilani sometime, sir. So.
Can I put the message? We are going to start. We are starting.
Yeah, I'm ready to start, sir. Let me know once the participants have joined in so that we can start.
Uh, 29 participants are already there, Vineet. We can start. I have put the message also. It was 10:40 and it is...
Okay. Sure, yes. I'll start, sir. I'll start. So the way we saw in this program, I just go to my last program which we created together. This one. Basically, we had the case structure which had only two cases, true and false, because a Boolean can always be true and false. What if I don't have a Boolean here? I have a numeric control as a input for the case structure. Okay, let me change the representation of this to be integer. Okay, and then I connect this. What happens when we do this? Now, as soon as I add numeric control as a case selector terminal, what can be the value of this numeric control? It is an I16 number. Now, an I16 number can go anywhere from minus 2 to the power 15, 2 to the power 15, all the way up to 2 to the power 15 minus 1. Am I right? This number can be, this integer number, I16 number, can be anywhere between minus 2 to the power 15 to 2 to the power 15 minus 1. Yeah. Am I right or wrong? Okay. Let's say if it can go to these many values, are we going to write a case for every value? Is that practically possible? Because this is going to be more than 65,000 values. Will I write a case for 0, 1, 2, 3, 4, 5, all values? No, it's practically impossible. So while you connect a control or an indicator, a control to the case selector terminal, which can have multiple values which can have multiple values, and if you're not writing a case for each of those values, then you have to define a default condition. So if you look at, we have 0 as a default here, and then there is 1. So if this numeric control has 0, then it goes into the 0 case. In 0 case, subtraction happens. Okay. If you have 1 as a numeric control, then it goes into case number 1, which is addition. Anjuna, you have a question? Hello? Anjuna, I can't hear you. Your voice seems to be distorted. Is that a problem at my end? Hello?
I think problem is Anju.
Do you mind typing out your question under the chat window, ma'am?
I think something is there in the chat. I'll let you know.
Okay, I'll continue in the meantime. So if you put 0, this goes into the 0 case. If I put 1 in the control, it goes into the first case. And if I put 2, which case it will go into? Can anybody comment?
The default one, that is 0.
It will go into default. You are right, sir. It will go into default. What if I don't define this default? Let's say I go here and say remove default. Okay. If I remove default, LabVIEW will not let me run this program. It will say that if there is default, if there is no default value, then it does not know what to do when somebody enters 2, 3, 4, 5 or any value greater than 1, because the case is not defined for any other value than 0 and 1. Hence, it is very important for us to make at least one case default while we are putting a control which can have multiple values. Is that clear? Okay. I have a question here or a problem statement, which is as a homework I'm giving. Please make a program for a calculator which will do addition, subtraction, multiplication, and division. It should also take care of the division by 0 scenario. Okay. So please create a calculator based on LabVIEW for addition, subtraction, division, multiplication. We will deal it tomorrow as the first thing tomorrow morning, that program.
Sir, means for this same one, we need to add division and multiplication. Am I right, sir?
You have to add division, multiplication. Secondly, I should use only run button, not the run continuously button. So you will have to use while loops, etc. Also, you will have to take care of division by 0 scenario. You cannot divide a program or you cannot divide a number by 0. Right?
Okay, sir. I will try, sir.
Okay. So that's a problem statement given for home. I will quickly jump on to the next topic for today, which is debug tools in LabVIEW. Now, Parikshit sir had mentioned about execution highlighting, right? This one. So if I switch it on and run the program, I can see each of the values flowing in the wires, right? I'll do that again for you. If I put this execution highlighting on and run this, I can see this values going through and passing through. So I can figure out where my logic would have faltered. Debugging tools are used to find out errors or issues with your logic, right? Another tool for debugging is probes, right? We can probe at various places, right? So what I'll do is I'll remove this execution highlighting, put this whole thing through a while loop. You need not do it with me. You can just look at these techniques, right? So I'm creating a while loop so that it runs continuously. It runs continuously, right? And I will add a probe here. Let's say I add a probe here. Okay. I have this probe. I'll run the program. I will continue to see value in this probe window. Yeah. Let's say I want to add some more probes. I can simply go on the wire and click to add another probe. So probe shows you the real-time value updated every second. Right? I can, let's say, probe at various other places. You can see all the probed values. It tells you probe number 1 is giving 5 value. So probe number 1 is here. So that means this wire has currently value 5. Okay. Probe number 2 is giving value 3. So this wire has value 3 right now. Yeah. Now, somebody asked a question today morning. I think it was Raghav. He had asked a question, what is breakpoint? Now, let's understand breakpoint. Okay. Let's say I want to check my logic. So I create a breakpoint here. So how do I create a breakpoint? I go to the wire, right click this wire, and breakpoint, set breakpoint. Okay. That means program will come and halt at this position. It will only execute further once user asks the program to move further. Right? So let's see, this is a red colored boundary here. So that means it will come and halt here. So let's run this. So you can see the program is waiting here now. So I can quickly check my probe values if my values are as per what I had expected, right? So A has 3 value, numeric control has 22, and B has 2 value. Okay, let's say these values are correct. I press on this pause button to move forward. It completes one execution, comes back, and again waits here, right? This while loop is running, but every time execution comes and holds on to this breakpoint. Is that clear?
Yes, sir.
Now, few more things. These was the execution highlighting, probing, as well as breakpoint are 3 debugging tools. There is another option of retaining wire values. So if I close the probe window, all the probes will be removed. Okay, you can see all probes have been removed. Now the breakpoint is simply on the wire. I can switch on something called retain wire values. Okay. Now the program is right now waiting here. That means these wires have already executed or data has already flown through these wires, but I will still be able to probe. Okay, once it runs, then I will be able to probe and see their value. Okay. As a homework, I would suggest one thing. I'm giving another homework because we are slightly off the schedule for today. So in LabVIEW, you can simply go to help. Okay. Go to help, LabVIEW help, and search for retain wire values. Okay. And look for a help window, look for the help of that function for retaining wire values. Let me check where it is. Okay, just give me a moment. Please. I think it's just give me some time. I will share the reading material for this maybe by the afternoon. So read about retaining wire values as well as the single stepping functions. So there are like 6 to 7 debug tools in LabVIEW. One was the execution highlighting. the other one was probing, the third one was breakpoints, and then there are these four, the retain wire values and single stepping. I will share reading material for these. Please read this once today evening after the workshop, and we can discuss this tomorrow morning again in our session. Right? Is that clear?
Yes, sir. Sir, may I ask that how this breakpoint means help while actually creating the applications?
Okay. Let's say this program is running continuously, right? This program is running continuously, and I feel the results are not proper. Okay. This is a very small program right now, so we can easily figure out. But let's say if it's a large program, very large program, and there is one output which is not coming properly. Okay. Then what I can do is I can add probes here. Okay. I can add probes here and set breakpoint to this position. Okay. Add another breakpoint at this position maybe. Okay. So, and we can add a probe here as well. Okay. So while I run this program, okay, you will have enough time to go through your probe values to check whether everything is okay till this point or not. If I don't add this breakpoint, this will keep running continuously. And let's say in a real world scenario, these will not be constants. This data will be coming from some signal. This data will be coming from some real world signal, let's say temperature, pressure, digital input output, or some value which is continuously varying, right? So if I don't stop the program here, I will never find time to calculate and see if the logic written is correct or not. So breakpoint just halts your execution at one place so that you can look at your probe values to comprehend whether my logic till this point is correct or not.
Yes, sir. Divide and check policy. Got it, sir.
Kind of, yeah. While I see that Raghu has already put in the debug tools link in the chat window. So take that as a homework, take that link as a homework, bookmark it, do read it, and we will discuss it tomorrow.
Yes,
Yeah?
sir. Bookmark, sir.
Okay, great. Now, I am finishing. I believe that we have dealt with the debugging tools as well. I have given two homeworks. One is building a calculator and reading the debugging tools, reading about certain debugging tools. I will hand it over to Raghu, who will talk about data acquisition. Whatever we have not covered from today's agenda, which is accessing help in LabVIEW and file handling piece, I will either deal it just after Raghu's session or deal it tomorrow morning. Don't worry, we will finish these two topics as well. Okay, so with this, I'll give it to Raghu.
Sir, actually, I think help should come at the last, right, sir? After performing all the operations, means if we have any questions or doubts, I think then we will attempt for help. I think it should come at the last, right, sir?
Help is a very important feature while you build a program itself, right? LabVIEW has more than 30,000 pre-written functions. Now, nobody in the world can really remember each and every function, right? And
Yes,
nobody in the world can really remember where exactly the function resides on the controls or the functions palette. So accessing help is not bad. Accessing help is very important while you write a program. So before we get into interfacing these hardwares, we need to understand accessing help piece. Otherwise, we will keep making some mistakes, right? So we will cover it, maybe not at the end, Naveen sir, maybe at the beginning before we get into hardware interfacing. All right?
Sure, sir. I said it in general. I think, yes, sir, you are right, sir. Thank you, sir.
Thank you, Naveen sir. With this, I will give it to Raghunandan to take you through concepts of data acquisition.
Sure, sir.
Raghu, would you want to take over?
Hey, Vineet, can you hear me okay?
Yes, Raghu, I can hear you.
Okay. All right. So thanks, Vineet, for having me over. And hello, everyone. I'm sorry I wasn't able to join in at the very beginning of the session today. I had some issues with the laptop. But yeah, I'm here to talk a little bit about data acquisition. So for the next 20, 25 minutes, we will talk in general about the principles of data acquisition and what are the things you need to remember. And then once we move from there, I think you will apply most of these concepts when you do the real world use cases with LabVIEW, whatever we need to be covering just after this. So let's start with a quick question for everybody. I know I've got a data acquisition definition on the slide right now, but I'd like to ask for everybody in the chat box, if you can, to take a minute to probably put in applications where you think data acquisition is important or where you think data acquisition is happening in real time around you in a day-to-day environment. I possibly can't monitor the chat box because I'm in the presentation mode, but in case there are people who would like to unmute and speak up, I'll be happy to hear. So where have you seen data acquisition systems in real life? And probably every day around each of us there are enough.
In any process industry, wherever we are having number of variables, which can change at any moment of time and can affect the whole process, the people are using this data acquisition system or data logger system so that they can keep track of the data. Either it can be temperature, or it can be pressure, it can be volume, it can be some other quantity, raw material weight, or etc. Like in textile industry, in chemical industries, process industry, cement industry, and many other process industries where we are processing the material and convert it, like in zinc smelting plant, etc.
Okay. Any others who would like to talk about data acquisition systems around them?
So the VR gaming systems.
Okay, VR gaming systems. Okay.
So the positional data of our positional data has to be taken care of. So that is one place.
Right. Okay.
I think this online webinar also there is a data acquisition and processing.
Yeah, I think that's a very interesting application. So yes, my audio is coming to you after being acquired by my microphone. It's all digital data which is coming to you over the network, and then you have the data generation happening on your side, which is the digital data being converted to the audio signal, either over microphones or your computer speaker, you're able to hear it. So that's a very interesting application. I'm sure everybody is using smartphones, so you have a microphone, you have a speaker there, you have, in some ways, you have your touch. I'm guessing everyone's using a touch screen phone. So all of those are different ways in which you're bringing in data into the system. Now, why is it important to have data acquisition? Because today, most of the processing nodes that you would talk about are all digital. And not every signal that you have around you is in digital, so I cannot directly interface, or the processing node cannot directly interact with the physical world outside it. So the first step that we do is basically bring in all the data in the physical world into a form which the processing node can take up, work on it, apply the processing, the existing processing power, the algorithms that you would have, and based on how you would like to visualize or how you would like to interact with the physical world again, you would have the output from the data acquisition system. So anything where you're able to see a physical world system being connected back to a processing element, that's a classical example of where data acquisition is happening. Okay, so it could be your laptops, phones, it could be your smart speakers, it could be in some ways your television because it has an IR input. It could be any of these other places. Now, it's not necessary that the data has to be just analog. It could be digital also. Now, in some places, you may have digital data also, which you want to bring into the processing node. So there also, it could be data acquisition. Okay. So at a high level, basically data acquisition is it's the process where you're bringing in all these electrical or physical phenomena around you into a world where the computer or the computing environment can interact with it. Now, based on the different sorts of signals that you want to bring in, you would have different sorts of sensors or transducers which can allow you to bring in or from the computer send it out so that you're able to interact with the physical environment. Now, we've talked about data acquisition. So what sort of signals, the primary classification of signals that you could have when you talk about data acquisition devices. So you typically have the digital data or the analog data. Now, the digital data, like everyone knows, is discrete in time as well as in amplitude. So here you see I've got 4 lines which are showing you digital data. It's a burst of zeros and ones. And then on the time axis as well, you would see a visualization which talks about how this transition is happening between zeros and ones. Okay. Now, when we talk about digital data, there are a couple of important parameters or important terminology that we typically use. So here is a group of terminology that we use. So we have something called as a bit, you have a byte, you have a line, and you have a port. Now, bit is basically that smallest unit of data, either a 1 or a 0 that you would like to process or you would like to act upon. Now, a byte is basically a collection of bits. Typically, we refer to a byte as a collection of 8 bits which are related. And this is one amount of data that you would have. So 1 byte of data is a very common notion of the amount of data that you've got. So today, when you talk about digital storage or your laptop storage or your phone storage, you talk about bytes of data, multiples of these bytes of data. So you talk about megabytes in terms of file sizes. You're talking about gigabytes in terms of storage capacity. And when you're talking about these very large applications with big data and AI and ML and all of those cases, you're talking about much larger cases, which could be terabytes or exabytes. Those are just multiples of this bytes of information that you're talking about. Now, this signal, whatever you're trying to acquire in a digital domain, would come to you over a line. This line is basically any individual component which is bringing you that actual data, digital data from point A to point B. Now, a collection of lines becomes a port. Now, typically these ports could be a collection of 8 bits of data, or it could be 16 or 32 bit, which means you would have 8 lines which are bringing in digital data at a particular speed, or 16 lines or 32 lines which are all related together. So you would want to process them at a common place. You don't want to separate them out because the information between them is related. So you'd want to process those 8 bits or 16 bits or 32 bits of information together. Okay. Any questions on the digital piece of it so far? Okay. Now let's move into the other portion, which is the analog signals. So an analog signal is a classical representation of a signal, which is a sine wave. So an analog signal in many ways is continuous. So it is continuous in time as well as in amplitude. Okay. Now, the importance of data acquisition here is that I want to capture this information in its truest form and bring that into the processing node or the microprocessor, microcontroller, variety of these processing environments to make sure I can do some computation on this and understand what this signal represents, right? So it's continuous in time as well as amplitude. So I want you to remember it's both. It's not any one. It is continuous in time and amplitude. Okay. Now, the common terminology that we use with an analog signal are these 3. So you have a level, which is the instantaneous value that the signal is at any given point. Then you have the shape, which is basically the overall envelope, if I were to talk about it, or if I look at a particular time period in which the analog signal is observed, how does it look like? How does the amplitude envelope look like? So that's what the shape would be. And then I have this frequency, which is basically what is the number of occurrences of, let's say, a repeating event within the signal. So if it is, let's say, there is a crest and a trough like a sine wave, what is the number of occurrences that I would have in a unit amount of time, right? It could be 1 millisecond, 1 second, 10 seconds. Now, basically, I would normalize with respect to that, and I would have a frequency domain representation, which is typically through the Fourier series transforms or the associated computation mechanisms. Okay. Again, any questions on this when we refer to level, shape, or frequency? Okay. Now, moving forward, we have these 3 R's of data acquisition that I'd like to refer to. So we are talking about an analog signal which needs to be brought into the digital domain. So we talk about three major points that we want to take care of. So one, which is the resolution, the next point, which is range, and the third point is rate. Okay. Now, what is resolution? Okay. Now, if I were to represent this sine wave, I have a single cycle of this sine wave which goes from 0 to +1, then goes to 0, and then I have the trough which goes to -1 and then back to 0. In this case, the amplitude is scaled with 10, so it goes between 0 to 10 and then 0 to -10. Okay. Now, if I were to represent this in digital domain, remember it would be digital domain which is both discretized in amplitude as well as the phase, or sorry, the time. Now, for the next couple of slides, don't worry about the time piece of it. Just worry about how do I discretize this in the amplitude space of it, right? So I would take a couple of bits and I would start sampling, or I would start looking at points where I can truly represent this. So if I take the example of a 3-bit representation, so if I have 3 bits representing the amplitude, then this is how my approximation would look like. Okay, so 3 bits gives me how many amplitude levels? Hey, can everyone hear me okay?
I can hear you.
Okay.
Yes, we can hear you, sir.
Okay, so yeah, it's just a question for all of you then. How many levels would I get with a 3-bit resolution?
8 levels.
8 levels.
8 levels, right? So because every bit can take either 0 or 1 or 2 states, I have 3 bits which can take 2 states each. So there are 8 combinations possible. So that gives me 8 amplitude levels which I can use. Now, what I typically use is basically the resolution, or the number of binary levels that I can have with a combination of bits would become 2 power n, where n is the number of bits that I would use in a resolution, right? So if I simply double this, and if I look at, let's say, a 6-bit resolution, I would have 2 power 6 number of amplitude levels against which I would be quantizing, or I would probably be representing the sine wave, which is purely continuous, right? So this is how the green line would look like. Now, against 2 power 6 levels, I have a lot more resolution. So I have 6 bits representing instead of 3 bits, which means I have a lot more amplitude levels against which I'm looking at it. So my sine wave would have lesser error when I represent it in the digital domain. So clearly, the more the resolution, the better it is for us. But again, when you impose the constraints of the processing as well as the data transfer between point A to point B, you realize that you always have this trade-off of, if I have very large resolutions, let's say I have 10-bit, 12-bit, 16-bit, 18-bit, 24-bit, or 28-bit, larger the bit resolution, the more the processing intensive it becomes. So there's always a trade-off in terms of how complex is my processing versus what is my bit resolution. And typically that's what the system engineer on a particular product design team would be doing. He would be weighing what would be the option of, hey, how important is this resolution for me versus how important is the speed of computation or the resources for computation, and then make a call. Okay. Now the next piece that we'd like to talk about is the range. Now the range basically represents at a very high level what is the swing in the amplitude from the maximum to the minimum on a sine wave. So again, I've got the single sine wave cycle. Here the range would represent that it is going to maximum of +2 and a minimum of -2. So my range here would become +4 volts for the sine wave. But if, let's say, I am actually looking at the acquisition resolution or the range, here it is between +10 and -10, which is the scale. So my acquisition range could be 20 volts because it is between +10 and -10, whereas my signal is only between +2 and -2. So this would mean that because I'm not matching these two well, where the signal is and where my actual acquisition range is, I would be missing out, or I would not have very good representation when I change it into a digital representation. Okay. Any questions on this? Let's move to this piece. That if I were to actually change that, now if I were to change the range from +10, -10 to, let's say, +2 to -2, now the same range is, I'm able to quantize it better in terms of amplitude levels with the same 3-bit resolution, because the entire range that I have for the acquisition device is very well mapped to the actual signal that I would have, and hence I'm using the entire dynamic range of between 0 to 3 bits to give me the range that I would, to give me the representation of the signal that I would like. I'm sorry about the background noises. I stay pretty close to an airport, Bangalore, so you might hear a couple of flights and helicopters passing by. I hope it's not too loud on the microphone. Okay, the third piece. Now, when we come into the rate, we're talking about how this is the time domain piece of it now. So the resolution and range, we talked about it in the amplitude piece of it. Now the rate primarily considers in terms of how do I quantize it in terms of the time domain piece of it, because the digital domain, a digital signal would be quantized in time as well as the amplitude function. So for rate, if let's say I have an original sine wave, which is 10 Hertz, which means in every second I would have 10 cycles. How do I make sure I have a good representation of this is what the rate piece of a data acquisition system would talk about. So we typically refer to this as the sampling rate. Most of you would realize that this is very closely tied back to most of the theory that we've studied around data acquisition and analog to digital converters. So the Nyquist theorem comes in here. So to give you a representation, I've got this visualization here. So let's say my original signal is 10 Hertz and I sample at 11 Hertz, which means I take for every 1 second, I take 11 samples. Now, if I quickly try to reconstruct the signal with 11 samples, this is how my reconstruction would look like, right? Now, you can very distinctly see that the signal which is represented by the white color as well as the red color are very different from each other, right? So how do I correct for this? What would I need to do with the sampling rate? Should I increase? Should I decrease? Should I maintain it the same?
Increase.
You should increase the sampling rate.
Okay. Now, what should I increase it to?
Double the original waveform frequency.
Okay.
At
Okay.
least. At least.
At least. Okay. That's an interesting word. So let's say I have doubled or slightly more than double. So I'm sampling it at 25 samples per second, which means I get 25 samples in time, which represent this 10 Hertz signal. Now, does this represent the sine wave well?
No, not that well, but comparatively better.
Okay. Now, what decides what should be the sampling rate?
Bandwidth.
Okay. So let's say I want to acquire, so you know Vineet has got this application of building a talking tom in the agenda for today. So let's say the talking tom requires you to provide your real-time voice input. So let's say you need to acquire your voice for, let's say 5 to 10 seconds. Let's say for now 5 seconds. So what is the signal that you would get? What do you think would be the frequencies of your audio signal, your voice?
So generally the human voice frequency ranges around 3.4 what is it? Hertz or
Kilohertz.
kilohertz? Yes, kilohertz. 3.4
20 to 20
kilohertz.
kilohertz.
Right.
So
So
that
20
is the audible thing.
yes.
Like 20 to 20 kilohertz is what we can hear. I am saying about what we can say.
Yep. So 20 to 20 kilohertz.
400. 300 hertz to 3400 hertz.
Yes, sir.
Right.
300 hertz to 2.4 kilohertz. Yes.
Right.
Exactly.
So 20 hertz to 20,000 hertz or 20 kilohertz is what the audible range is. And the speech range is typically between 300 to 3.4 kilohertz. So let's say I have a 3.4 kilohertz signal. That's the maximum that I have. So assume someone is talking at 3.4 kilohertz or saying some things which require 3.4 kilohertz of signal. Now, what should be the sampling rate that I need to consider? So if you were to choose a microphone, what would be the rate that I would consider for that system? So going by the earlier discussion, we need to look at something slightly more than double, right? So double of 3.4 would be about 6.8. Now, conventional microphones in your in your telephones would typically sample it about 8 kilosamples per second. Okay, so if you go back to your olden days telephone lines, your I would say landlines, those would have an 8 kilosamples per second sampling rate because they're slightly better than, or that sampling rate is slightly more than the 2 times the 3.4 kilohertz range. Now, all the background of this comes in from Nyquist theory. I don't want to talk a lot about that. But one piece that we need to remember here is that Nyquist theory was an exact, the theorem was an exact theorem, which means that anytime you sample above 2 times, you should be able to represent the signal well. But I think the important piece that we also need to remember is it depends on what I want to do with the signal beyond it. Now, if I want to bring it back to the analog domain, I would have this process of reconstruction, right? And most of you would understand that bringing a digital signal to an analog signal involves reconstruction, which uses a filter. Now, the filter's response on how sharp it is and how good the transition is would define whether I can just go with slightly above 2 times the sampling rate, or if I need to have a much bigger margin. Now, based on how good my reconstruction filter is, if it's very sharp transition between the passband and the stop band and has a very good alpha or the transition coefficient, then I can start pushing the limits towards 2 or closer towards 2 times the frequency of the signal that I'm acquiring. But if my filters are slightly bad, then I would need to start stretching that, which means I need to have at least 4 or 5 or sometimes even 10 times the samples to make sure I can actually reconstruct that signal well. So for audio applications, because we've been doing it for so many years now, the filter designs have improved so much that we can start pushing it towards that 2 times. So 3.4, the double the rate in terms of sampling would be 6.8. So we're able to push it or have, let's say, 8 kilosamples per second as the sampling rate and still get a good voice between point A and point B when we have a phone call. But let's say if you had some other sort of signals, then you might have to relax that based on how good my reconstruction filter would be, right? So coming back to this now, at 25 hertz, I can reconstruct this. This is still going to be a good representation for 10 hertz, but then I need to have a very good filter. But in case my filter and the reconstruction is not as good as I'd expect it to be, then I can always go, let's say, up to 10 times, and this would be, let's say, I sample it 100 samples per second. Then this is how my signal would look like. So this is, in general, a very good representation as is. So I'm easing out the constraints on the reconstruction portion. So again, here is a trade-off where you can decide how good your A to D portion is based on how good my D to A portion is. So the analog to digital can be relaxed if my digital to analog converter is very good, or the vice versa. Okay. Now, this was the background theorem. So most of the piece, we come across this phenomena called as aliasing in case we're not able to sample the signal well. Now, the aliasing is basically I'm not getting a true representation of the signal because I'm not able to get a fair amount of samples that represent the true time domain signal. So aliasing happens where my sampling is not enough for me to represent the true time domain signal. Now, typically aliasing occurs when I'm not meeting that 2 times or that restriction of 2. In most cases, when a person is deciding on a data acquisition system, he would want to make sure he understands the signal that he would acquire, he understands the frequency response of it, and then make sure he at least has a good margin in the acquisition side so that he doesn't have this aliasing problem. But if this knowledge or this prior know-how of what the signal I'd be acquiring is not available, then there is a chance that you may be running into this aliasing effect, and hence it's important to be vigilant for it. So what happens in aliasing? So if I have a 100 watt signal, and if I didn't know I'm actually acquiring a 100 watt signal but sampled it at 100 samples per second, I would have an alias signal which looks like a true DC signal, which is not the true representation. Versus I have a 100 hertz signal sampled at 200 samples per second, I would get a triangular waveform. Again, if I better the filter, I would start getting a good waveform, which starts looking closer to a sine wave. Versus if I have a 100 hertz signal sampled at 1 kilo samples per second, I would have both adequate samples on both the frequency as well as to capture the shape well, without having too much of a constraint on the resam or the reconstruction portion of it. Okay. Any questions so far on this? This is important for you to know because every time you talk about a data acquisition system, go out in the market or try to build a data acquisition application, this is the first thing that you need to worry about. What is the range? What is the resolution? What is the rate at which I need to acquire? And there needs to be a prior know-how of what your signal you're trying to acquire would be, so that you can choose a system which can give you the appropriate performance in range, resolution, as well as rate. So if there are any questions, I'd request you to unmute and speak, or even put it in the chat box, and we'd be happy to answer.
Hello, sir. Is level and triggering work in same manner?
Ma'am, your voice cut off in between. Could you please repeat the question?
Is level and triggering work in same manner in that card?
Okay, so level and triggering is the question, right? So how does level and triggering work in that card?
Yes, sir.
Okay, so think about it this way. Now, a level would represent, if I just go back a couple of slides, a level here would represent what is the representation that I would have here. So if I have a 3-bit, the level would be based on where I quantize it to. Okay. Now the triggering portion of it is slightly later. When we talk about, if I want to have an acquisition system which doesn't acquire all the signal that comes to it, but only acquires it around a particular event or a particular case where, let's say, the signal which I'm expecting on the line connected to my data acquisition system is having an unusual occurrence, then we consider a trigger for that. Now, a trigger could be digital or analog signals. If I have a digital signal trigger, then it would be a pulse that I'd expect on it. If I have an analog trigger, which what I would have is a trigger which is configured based on the value. So how the analog trigger would work is if, let's say, the level goes above a particular, let's say, a particular pre-configured threshold, then the triggering happens, which means that the output of the ADC would now be passed on to the next stage, which could be the processing or the logging function to carry out subsequent action. Right? Did that answer your question?
Yes, sir.
Okay. Any other questions? Okay. Everyone's clear with range, resolution, and rate? It's good to have feedback so that we are calibrated on where we are. So either a yes in the chat box or unmuting and speak would help. Okay, I see one yes. The last time I saw there were 36 participants, so I can wait for at least a couple more responses. Okay, 2 people, still 30 people, 30 odd people still on the call. 3.
Sir, no questions yet, but I think we may get some doubt when we get to practical sessions.
Okay, all right. Okay, sounds good. So let's move ahead then.
Yes, sir.
So we've talked about the range, resolution, and the rate of acquisition. Now I'd like to talk about one other piece before I pass it back to Vineet, which is something which you refer to as signal conditioning. Now, signal conditioning is basically a pre-processing function that I'll be doing to make sure that I get the best of the signal that I'm bringing from analog to the digital domain, right? So consider your voice. Again, when you think about the talking tom application while we are going through some of these slides. So when you're speaking from the microphone, how many times have you not heard? So let's say the same use case where I'm living, you heard the background noise of the helicopter passing by. So that's noise versus my speech or what I'm talking is the signal for you. So the idea with signal conditioning is to make sure that the signal of interest gets the maximum attention when, let's say, the noise and the background effects in which the signal is being acquired is actually reduced as much as possible so that you're spending most of your time and resources either for logging or for processing on the signal which is of interest to you. So if, let's say, I'm building the talking tom application, if someone in the background is speaking something else, you'd want to try and attenuate or reduce the effects of that person in the background. Or if the helicopter is flying over, I want to reduce the effects of how much the microphone captures that. So these are all the pieces that I want to do in signal conditioning to make sure that I can bring that signal in to the digital domain in as reliable a manner as possible. Okay. Now, before I touch upon signal conditioning, one piece I'd like to touch upon is that you have these sensors and transducers, which are basically those elements which convert any physical domain signal into a representable signal which you can acquire. Okay. Now that representable signal that you can acquire is either going to be a voltage or a current signal. Okay. So a sensor.
Sir, I just need to share that nowadays means noise cancelling earpods or headphones are coming now, sir. They all comes under this section, right, sir?
So yes, in some ways, they obviously have a lot of acquisition and they have a lot of signal conditioning, but they also have a lot of processing that goes on, which makes sure that they can provide you that noise cancelling effect.
Yes, sir. I just wanted to share it. Thank you, sir.
Okay. All right. Now going back. So yes, you had a voltage signal or a current signal that you want to acquire. A sensor, in essence, is going to translate any of those physical phenomena. It could be force, it could be strain, it could be temperature, it could be pressure, it could be acceleration. So sensor is responsible for translating any of those physical parameters into voltage or current so that your data acquisition device can pick it up. Okay. Now, when I'm doing that conversion process, there is some amount of signal conditioning there also. Now, I will touch upon some of those use cases in the subsequent slides, but it's not an extensive list. And we've had to cut out a couple of slides in the interest of time because we're slightly behind. But when we share the slides offline with you, we'll make sure we plug in some of those as well. If there are any questions, you can reach out to us offline and we will have a discussion about it. Okay. So in essence, basically what signal conditioning is aiming to do is making sure that you can improve the quality of the signal of interest that you're trying to capture and reduce the other background effects or noise or any interference that may be occurring in between. Okay. So if I have a noisy low-level signal, my signal conditioning efforts would be to make sure it can be scaled and amplified and make sure I can reduce the noise. So here the signal conditioning would be filtering and amplification. Okay. So I'll touch upon a couple of them. Most commonly cited signal conditioning use cases for voltage measurements could be things like excitation, could be things like amplification or attenuation, could be filtering or isolation. I'll touch upon the middle two. I'll share the slides for the other ones offline and you can have a look at them and let us know if you have questions. Okay, so let's go into the amplification piece of it. So I have a very small signal, a very low amplitude signal. So my amplification basically amplifies this and gives me a better signal. So what I'm essentially trying to do is, if you remember the earlier slide here, you remember that if I have a low amplitude signal and if I directly don't match the range of the signal with the range of my acquisition, I will be losing out how well I'm representing the signal with my 3-bit resolution data acquisition unit. So what I'm going to try and do is make sure I can match the range. So what will happen is once I match the range, the signal gets amplified and then gets matched to the input range of my analog to digital converter or the data acquisition unit. And there my 3-bit resolution is getting fully utilized or well utilized to capture the data that's coming in through this physical world signal, right? So the amplification is to make sure this happens. Attenuation is the reverse, where I have a very large signal and I want to acquire it. So think of the use case where I want to monitor single phase current or voltage. So that's 230 volts. It could be rated at 10 or 15 amps. So bringing that in directly to a data acquisition device may not be possible. So I want to attenuate some of those signals. And here an attenuation is playing the reverse role where it is bringing it back to the range of the data acquisition device so that I'm able to use the entire resolution to make sure I can capture this or represent the signal in the time domain. Okay. The next piece that I'd like to talk about is filtering. So let's say I have a signal which looks like this. If I look at the frequency domain, I notice I have 4 peaks. Assume these 3 peaks were not of interest to me. So assume these 3 peaks are not of interest to me, and only this is of interest to me. So what I want to do is basically remove these three. So I pass it through a low pass filter and I have this pure sine wave signal with only the signal of interest being maintained. Okay. Any questions on this? Okay. So now when you're building the talking tom application, what are the use cases that you, sorry, there's a question, go ahead.
What is the difference between this filtering and the signal conditioning? Is there any difference?
Yeah, so Deepak, I think your voice is a little feeble, but I think I got the question. So your question is, how is filtering different from signal conditioning? So filtering is a type of signal conditioning. They're not different. Signal conditioning is anything that I would do to make sure my signal is good for me to be acquiring it. And filtering is one of those things that I could be doing to make sure I am only capturing the signal of interest and not everything else. So
Okay, sir.
filtering is a kind of signal conditioning. Okay.
Yes, sir. Yes, sir.
Okay. Now let me just quickly switch to just a second. Okay, let's do one piece. So we've covered all the topics of the data acquisition in concept. So before I hand it back to Vineet, I'd like to just put all of these concepts into perspective with the Talking Tom application, just to make sure you understand where each of these things come into picture. So just give me a minute. I'll just switch to a whiteboard. Okay, do you see my whiteboard?
Yes, sir.
Okay. All right. So now let's say you've got this Talking Tom application where you are the speaker. So your voice needs to be captured. So we talked about the frequency range of your voice. So it is between 300 to 3.4 hertz. Okay. So the sampling rate here would be how much? How much is the minimum I need to have for the sampling rate?
Please double.
At least double. Okay. So like we discussed earlier, so let's assume we take minimum 8 kilo samples per second. Okay. So this is my sampling rate. So we talked about rate. Now the resolution, okay, of acquisition. What would be the resolution of acquisition? How many of you have seen specs of your sound cards?
Sorry, sir. What did you ask?
How many of you have seen the specifications of your sound card?
No, sir. I have not seen that.
The CD, the CD is being written at 44 kilohertz, I think.
Yeah. So yes, so what we have captured is greater than 8 kilo samples per second. So when we talk about audio applications, typically 44.1, 22, 48, 96. So one of these, based on typically audio applications recording, happens at these, because they're not talking about just the voice, they're also talking about any music that you may be having. So here, because the speaker is going to speak at this, it will be between 300 to 3.8. So if I just have audio from a person speaking, then this should be okay. But if I have music, because the upper frequency goes to 20 kilohertz, I need to pick among these. Again, 22 is not the right one. 22 is better suited here. So I typically have 44.1, 48, or 96 kilosamples per second. Okay. Now, sound cards typically are rated for any one of these cases. 44, 48, or 96, based on what grade and what quality. The resolution of these devices would be typically 24-bit on the acquisition. In some cases, you may have lower also. So you may have 14, 18. In some cases, you may have 12 also. What does this mean? I will have 2 power n, where n is this. Okay. Is this clear? Any questions on this? Okay. So again, just coming back to the original problem statement that we had, you have 300 to 3.4 hertz. You need to sample greater than 8 kilosamples per second. So in the specific application, you will be using 22. You will be using a bit resolution depending on the audio card that you have in your system. So it could be 24, 14, 18, 12, somewhere in between. It could be 16 as well. But make sure when you open up your, when Vineet shows you the LabVIEW application, make sure you make note of this. And the range gets auto-configured. So what happens is your microphone is making sure your audio is well suited to the input range. So typically, these would be rated in a couple of volts. So it could be 2 volts peak to peak, or it could be other. But this is not exposed to you because your audio or sound card is already taking care of that. So you need not worry about this parameter. Your parameter number 3 is already taken care of. You need to worry about parameter number 2 and your parameter number 1. Okay. And again, these two would depend upon the sound card that you have in your system. Okay. Any questions on this? If you don't have questions on this, then I think we are ready to pass it on to Vineet, who will show you some of these in action.
Sure, sir. I think
Hello.
practical sessions will be helpful.
Okay.
Hello.
Ashok sir, do you have a question?
Yeah. Actually, I want to know the importance of signal ratio. We have not discussed in the whole process. We have mentioned that we require a sufficient signal to noise ratio, but how many levels or what is the bandwidth, how many number of bits we can use to represent a particular quantized data, does it affected by the signals to signal to noise ratio or not?
Right. Okay. So let's come back to this. So signal to noise ratio is basically a ratio which talks about signal power by the noise power. Okay. So what it would basically mean is, if I have, let's say, a 1 volt signal, and if I have a ratio which is defined here, it will tell me out of this 1 volt, how much of this is proportion to the signal and how much of this would represent the noise. Now, higher the signal to noise ratio, the better it is, because I have greater percentage of my quantized data, which is true representation of the signal of interest versus anything else, which is the noise. Okay. Now, if I have a signal to noise ratio which is low, what would happen if I have, let's say, signal and noise in equipartition or equal power? What would happen is that there is a good chance that this number is not a true representative of what was the signal that I originally intended to capture, because there's a large portion of noise or interference which is coming in and causing disruption. So if I use the same SNR with, let's say, a 3-bit quantizer or a 3-bit resolution, now the error which I would get would differ between a SNR which is low and an SNR which is high. my confidence would be better that I have a true representation of the signal with higher SNR values, because majority portion of the value that I'm quantizing is from the signal and lesser portions from the noise. So assume it to be a ratio of how much signal is there and how much noise is there, and how much of that is a true representation of what I really intended to capture in the first place. So if you have a higher SNR signal or a possibility to increase SNR at the start, then do that. So one of the objectives of signal conditioning is to make sure that you go from a lower SNR layer to a higher SNR region so that you're optimally utilizing the resolution of your card to get a good representation of the signal that you're looking at. Does that answer your question, sir? I didn't go into any mathematical numbers which I plugged in here. But
no, mathematical I know. Theoretical I just want to clear. Means if you are increasing the number of bits.
Yes.
Hello?
Yeah, go ahead, sir.
If you are increasing the number of bits through which we can represent that data, will it help in increasing the signal to noise ratio?
Are you talking about the SNR of the system or the signal itself, sir?
I think system.
Right. So your SNR of the system would definitely become better. Your signal would remain the same as what the original signal is.
Okay. Okay, sir.
So your SNR
Thank you.
of the data acquisition device, or that A2T that you are using, would differ, would change. So for ADCs, we have this typical number representation, which is your SNR is 6.02 into N. Your N is the bit resolution that you have. Again, this is in dB, by the way. So if I have greater N, then I have better SNR for the system. Again, this is ADC system SNR.
Okay. Okay, sir.
Okay. Okay.
Thank you.
All right. I think we've covered all of what was required, the background, the theoretical portions required for you to go into the practical pieces. So I'll probably pass it on to Vineet, who would show you a couple of things. So Vineet, over to you.
Thank you, Raghu. Thanks for taking us through this session. I will. What I plan to do next is we are at 12:54 right now. I want to spend another 35 minutes and then break for lunch. Is that okay, everyone, or would you want to break now?
It's okay, sir. I think till 1:30.
Okay, great. I think if anyone has a problem, please feel free to mention it on the chat window now, so that we can consider it. Otherwise, we will move ahead with the session. Okay. So what I'll do next is, I think everyone is okay with this session. I don't see any response in the chat. So we'll go ahead and discuss accessing help in LabVIEW. Then next we will interface Arduino and then start building our application for Talking Tom. Yeah. So let's understand, how do we access help in LabVIEW? There are various ways of getting help in LabVIEW. So let's say this is my front panel and the block diagram. I want to, let's say I want to figure out, I've placed a function on the front panel. I want to figure out what this function does. I don't know what this function does. So I quickly want to know about it. What I can do is I can go to help and say context help. Yeah, Parikshit sir mentioned about it yesterday. You can get context help about this. This context help window will give you help about anything you hover your mouse over, right? So let's say any function I place, instead of this function, let me place another function. For example, this one. So it will tell me about what this function does. Now, let's say if I want to have detailed help, this help, whatever is there on this window, is not enough for me, right? I want to have detailed help. Then I can click on this question mark, or can go to this, click on this button to get detailed help about this topic. Yeah. So you can see this detailed help about this function, which I have placed on the screen. So to access context help, I can go to either help, click context help, or simply press Control H on your screen. Control plus H, H for Himachal, and you will get this context help. Yeah. And for detailed help, you can click on detailed help. Right. Another important aspect of help is to find out where my functions and controls really are. How to find that? On the block diagram, let's say I want to find out a function, you can simply right click, you get the functions palette. Instead of scrolling and really finding out in which palette what function is available, you can search here on the top. Right? As soon as you search here, let's say I want to acquire sound, I can simply search. It will take me to where this function exists in my palette, in my functions palette. Is there a question? Raghu, your mic seems to be on. So now if let's say I want to search acquire function, I can simply right click, search for an acquire sound. Right? I'll double click, it will take me to the palette where the function exists, acquire sound. Right? Now, how is it different from context help window?
Sir, did you enter the shortcut key, or how did you open that search palette dialog box, sir? I did not get that.
Okay. So right click on your block diagram, you get a functions palette, right? On the functions palette at the top, there is search.
Oh, okay, sir.
Okay. And if you type in there, you can find your function.
Yes, sir. Got it, sir.
If you double click this, it takes you to the location in the palette where this function exists, right? How is it different from context help window? In the context help window, let's say if I press Control and space bar, sorry, not context help, quick drop. If I press Control plus space bar, I get a quick drop window. How is it different from quick drop window? If I type acquire sound in the quick drop window, I can directly place this onto my screen. Right? Whereas
yes, this is better than search palette, right, sir? I mean, more applicable and easy.
Yeah, the quick drop window is easier to use because I can directly find a function and place it onto my screen, right? Whereas this search palette, where it is useful is, let's say I don't know my exact function which I want to use, right? But I want to explore other functions which are similar to that, right? Let's say I want to practice something on the filtering side, right? So I can go to the palette of filters, right, which is right now under image processing, right? So I can look at various other options available and choose the right one, or pick and choose from these available filters. Does that make sense?
Yes, sir. Means both are unique, sir. Means while working, actually quick drop really helps to just drag and drop. But this one means we can just means separate by the categories, sir. Got the point, sir.
True. Yeah, you can just look into various other options available for a similar function, because in LabVIEW palette, functions are categorized based on their functionality. Yeah.
Yes, sir.
Okay, so we learned about context help. We learned about how to go from context help to detailed help. We understood about quick drop window. We understood about search. Let's understand how we can directly go to detailed help. We can simply go to help and click LabVIEW help. Okay, in that, like I was about to show you in the previous session how to find about debugging techniques. So I will simply write debugging technique, and let's hope I can find debugging techniques right now here. Debugging techniques concept. Yeah. If I click on this, I have the help about each of the debugging tools which we discussed today, right? As well as for the homework which we have given. Single stepping features are explained, as well as breakpoints, probes, etc. Everything is explained. So you can read this paper or read this help file and understand more about each of these features. Yeah, that is another way of getting help. The last way is simply go to this search button, click on it and search for a function. Let's say I want to search for while. Okay. What it will do is it will list down all the help pages where while loop is used or while loop is mentioned. I can directly open that. It will take me to the help of the while loop. Okay. Or it can directly take me to the palette. For the palette, it tells me whether you want to drop a while loop. You can directly drop a while loop. Or if you want to find it in the palette. If you want to find it in the palette, it takes you to the palette. Right? Then it can also find support for these things from our NI support pages and community search. Right? If you click here, it will search it on the NI community and list down top few topics around this. Yeah, LabVIEW for loops and while loops explained. Yeah, if I click this, it basically opens this paper on the website. Yeah. So we have very comprehensive help available in LabVIEW to search and figure out about various functions and options inside LabVIEW. Is that clear, or you have any questions?
Crystal clear, sir.
Great, great. Now quickly let's jump into interfacing Arduino. What is Arduino? What is
Actually,
Arduino?
I have no idea about this, sir. As I said, I come from mechanical background. I think I need an introduction to this, sir.
Okay. So, do you understand microcontrollers, sir?
Yes, sir. Means we have read about it in basic electronics subject.
Great. So basically, Arduino is nothing but it's an open source hardware and software tool, which allows you to quickly prototype your electronic circuitry. This is based on an Atmega microcontroller. So this black chip you can see here is an Atmega microcontroller, and all the support circuitry to interface with inputs and outputs. Right. So basically, you can burn in your application or your program onto this microcontroller and control these inputs and outputs. Right. Now, this has around 13 or 14 digital inputs and outputs with an LED connected onto the 13th pin. On the Arduino Uno board, an onboard LED is connected to the 13th pin. Then there are TX and RX LEDs, which talks about any data, which basically blinks when there is any communication over RS-232 or USB interface. While the board switches on, it gives you power LED here. Basically, the power LED glows while the board is switched on. There is a reset button to reset the board in case if in your logic you're using the reset button, or if you want to power cycle the board. Then there are power pins wherein you can access 5 volt or 3.3 volt for your sensors from the board itself. You can also power this board either through USB power supply, directly connecting it to your computer, or put in an external 3.3 volt or a 5 volt input at Vin. You can also connect an adapter here, right, to power this board. Any questions?
No, sir. Actually, microcontroller 8085, that's the, I think, means the one which is taught to us, means it was the one which was included in the subject. Is it somehow related to this, sir? Means I don't think.
Very similar, sir. Like 8085, which was taught to you, is basically an older generation of microprocessors, or I would say first or second generation of microcontrollers and microprocessors which were introduced in the market. Post that, various other newer variants have been introduced. Now, while you build an application using your 8085 or 8051 or 8052 microcontrollers, you have to write the program in either assembly language or embedded C, right? And also have to prepare a prototype board on which you can mount the microcontroller, give the clock excitation, the crystal clock to the base clock for the microprocessor and the microcontroller, the power supply, and various other support circuitry. So instead of you building everything from scratch, Arduino has basically brought in that support circuitry onto a board and has made it available for a purchase. Now, let's say if you wanted to write a logic of maybe blinking an LED using 8085. So first of all, you would have to make the support circuitry. What would be the support circuitry? You'll have to give a clock to the microcontroller or the microprocessor. To the microcontroller, you will also need to provide power signals. And in certain cases, you might have to pull up or pull down the IO lines of the microcontroller. Right? Instead of you doing that from a scratch, a board is directly available for you, sir.
Yes, sir.
Okay. Now, this Arduino also has certain analog pins. These analog pins means there is an ADC, a 10-bit ADC, using which we can acquire analog waveforms. Right? Raghu mentioned about 3 R's of any data acquisition system. So what were those? Range, resolution, and rate. Yeah.
Yes, sir.
So the range of these ADCs, I think, is 0 to 5 volt. The resolution of these ADCs is its 10-bit resolution, and the rate is approximately 9 to 10 kilosamples per second is what max people have achieved on Arduino. Right? Okay. Any questions? Anyone? How many of you are using Arduino or aware of Arduino? Could you please say yes on the chat window if you've heard or used Arduino sometime? Okay. To the people who mentioned yes, are you interested in interfacing this with LabVIEW for acquiring data or generating data from this board? Okay, I got a couple of yeses, so I'll go ahead. Now, to interface with this device, first of all, we'll have to download a tool called Linx, Linx. Like you have your Apple Play Store and Android App Store on your phone, the same way LabVIEW also has its Play Store from where you can download various applications and packages. So what you do is search for VI Package Manager on your system.
Actually, it is installed in the system, sir. Means.
Yeah, I mean, VI Package Manager will get installed while you install LabVIEW. I mean, there's an option to choose, but the installation guide which I had shared, according to that, it was set to default that it will get installed, right? So once you open it, it may look something similar, may not look exactly same. I'm using a higher variant of VI Package Manager. You may have 2018 variant, but it will look more or less similar. Is everyone able to access VI Package Manager?
Means, do we need to open it right now, sir?
Yeah, you can open it. I can teach you how to install this.
Just give us a minute, sir. Sir, I think, please continue, sir. I think there is some problem here.
Okay, you might see it. It might not be opening if it is already trayed in your tray. So you can right click in your tray. There will be a VI, small VI icon here, and you can say open VIPM browser. If it is not opening, it might be trayed in your tray of your system. Okay. Anyways, I've also put in a chat. I mean, on the chat window, a small link to getting started with Linx. If you're not able to remember the steps we do now, yes, any question?
Sir, it is downloading some files.
The VIPM?
Yes, sir, it is.
It's not downloading, it is loading the files, sir. It is just checking your system for what all features are installed and what all features are not installed, right? So if you go here to VIPM, you can search for links, okay? If you search for links, you will find Vigilant links, okay? You double click this. Make sure while you double click, after you double click, the version of LabVIEW should be the version you are using. Right now in my system, I have 2020 and 2018 both. So I am choosing 2018 and there will be an option to install. Right now, it shows me an option to uninstall, but you can click on install in your case because it might not be already installed in your system, right? Once this is installed, okay, once this is installed, we can then go to the examples of this links library, okay? I will also post in the link where it will have the examples on the chat window. So the examples for LabVIEW are installed in your C drive. So go to C drive, program files, National Instruments, LabVIEW 2018, examples, and then I will search for Maker Hub.
Sir, sorry for interruption. Means we are setting up this because we as we need to integrate LabVIEW to the Arduino, right, sir?
Yes, this library helps you integrate Arduino to LabVIEW. Yeah.
Okay, sir.
Okay. I've also posted the once you install, you may not be able to install while we are talking right now. So I've also posted the the example folder location in the chat window. You can copy and keep it at your end because once you install it, you will find the links driver links example at this place. Okay. Now what I'll do is I'll go ahead and connect my Arduino to my system. Okay. I have connected Arduino. Then I'll go to I'll open one of the example programs. Let's say I want to blink an LED. So I will open Blink Simple. A program like this will open, right? Before running this program, I need to, first of all, deploy the Maker Hub firmware on my Arduino. To do that, I can go to Tools, Maker Hub, Links, and Links Firmware Wizard. A wizard like this will open, in which I can choose Arduino. I'm working with Uno, so I will choose Uno. Firmware upload method, I have serial USB.
Sir, is Arduino physically connected to your laptop, sir, right now? Hardware?
Yes, I'm trying to connect it. Somehow it is not detected right now.
Okay.
Okay, it has detected now. So Arduino is physically connected. I will show you once I open my camera. Now, once I have Arduino connected, I can choose the COM port on which my Arduino is available. Where do you find that out? You find out in your device manager of the system. You can see under ports Arduino Uno COM4. Okay. Now, once I've chosen the COM port, I can simply click next. It's asking me for firmware. I'm saying the default ones, and it's uploading a pre-built firmware on my Arduino. Okay. I would say finish. This firmware is installed. This firmware has to be installed or have to be uploaded only once while you want to interface your Arduino with LabVIEW. You don't have to do it every time. You just have to do it once before starting with LabVIEW.
Sir, actually, the link you have sent is means self what is that explanatory, right, sir? Means we can set up it, right, sir? As I have not followed these steps right now.
Yes, you can, sir. It will be very easily available. I will post 1 or 2 more learning resources. By the end of the workshop, you will have enough learning resources around links that you can do it on your own as well, right? But we just want to demonstrate here so that the basic principle is clear, right?
Okay, sir. I will check it out, sir.
Sure. Now, once the firmware is installed on the Arduino, I'll go ahead and interface it. So first of all, I'll blink the onboard LED of the Arduino Uno. The 13th digital pin of the Arduino is internally connected to the LED on board. So if I put the digital output as high, what will happen? The LED will glow, right? If I put digital output as low, the LED will not be forward biased and no current will be able to flow through it and LED will not glow. So let's try that. I choose COM4 as my COM port. I am choosing channel 13 as my digital output channel, and I will run the program. Okay, let it run. It's running now. Now I'll just switch on my camera for you to be able to see the Arduino. So how many of you can see 3 LEDs right now glowing on the Arduino? 2 of them are TX and RX LEDs, and 1 of them is the power LED.
Yes, sir.
Yeah. Now I will glow the 4th LED, which is the user control LED. As soon as I click here, can you see a 4th LED just beside TX and RX LED glowing up?
Yes, sir.
I will switch on and off. Yeah. So I'm able to control this on and off of the LED directly through the LabVIEW front panel. Okay.
Just with a single click, sir.
Just with a single click, right? Now, this was fairly simple. Like we access the example program. Now, what if we want to build our own application? So you need not do what I'm doing right now. You can just follow the simple. You can just look at the steps. These are again very well documented, and I will share the documentation with you. So just look at the steps I'm doing. Any questions? What we will do now is I have a potentiometer, a pot, which I have connected to my Arduino. I am taking a 5-volt supply from my Arduino. I'll just go to the diagram. So what I'm doing is I have a potentiometer. Potentiometer is nothing but a variable resistor, right? And I have connected in this fashion on my Arduino. Now, what I've done is I've taken a 5-volt power supply, which has gone to this pot. The ground is supplied from the ground pin, and the resistance. Once I rotate this knob, the resistance at this terminal will keep changing. Because resistance will change, the voltage drop will also change. So I will measure voltage at this pin through the analog input. Okay. Now let's see how to build a program for that. I will simply go to LabVIEW. Is the circuit clear to everyone?
Yes, sir.
Okay. Now I will simply I'll right click on the block diagram, go to Maker Hub. Under Maker Hub, there is links, and I will pin this palette. I will open a connection to my Arduino. I will go to peripherals, analog, and read from the analog channel. I'll go back and close the connection with Arduino. Okay. Now let's see what all controls it is expecting. So what all inputs it is expecting. So can I press Control H for context help?
Yes, sir. Control H.
It is basically asking for a serial port and the baud rate override. I'll just give the serial port baud rate. I want it to be default, and some error inputs and outputs. So I will right click this serial port input and create a control. So you can see this serial port control has been created. I will take this link. I will take this links resource wire and connect it to the next function. The output of the next function will pass on resource information to the next function. So typically the top output wire on the right corner is typically the resource information for majority of functions in LabVIEW. That means a serial port connection has been established and the information of that connection is being passed over this wire to all the functions. And the bottommost wire on the right side and the left side is basically your error wires. If there is an error information will flow through these wires. Okay. Is it clear?
Yes, sir. A bit of.
Okay. Basically, I opened the connection. While opening the connection, I need to tell which port my Arduino is connected to. So I have chosen that serial port here, then passed on the resource information to the analog read block and closed the connection. Okay. Now let me give the analog channel. There are 6 channels or 5 channels on Arduino which can give me analog data. So I have to choose which channel, and I want to see the voltage output. So I can create the indicator on the voltage channel. You are able to follow?
Yes, sir.
Okay. I will choose the serial port now. Okay. And run this. It is communicating with Arduino, setting up the connection, and will give us the voltage pretty soon. So this gives me 3.5 volts. Okay. What if I want to make this, I want to keep acquiring this voltage signal. I just now acquired only once and closed. What do we do to make the program run continuously?
Sir, there is a button, sir, next to the run. We can just.
Okay, you're talking about this button, sir. We use
Yes,
this button only in the debug mode when we want to debug something. But usually we use a function inside LabVIEW which helps us run a particular logic continuously. What is that function?
Sorry, sir, I am unaware of that.
The function is called while loop, sir. If you put while loop around this will run continuously, right? Until and unless user presses stop. Yeah.
Yes,
is
sir.
that okay?
Okay.
Now, okay. Is that clear to everyone what we're trying to do here? Yeah. Okay. Now, let's say if while I do this is fine, but there is one problem here in the program. The problem is establishing a connection with Arduino and stopping the connection or stop communication with the Arduino is a resource intensive task. That means it takes a lot of resources of your computer as well as time to establish the connection and to remove the connection. That is true for any hardware while you connect to your computer. So instead of spending that time every time, can I bring these two functions outside the loop? That means, let's look at data flow now. A connection will be opened with Arduino. Connection information will go over this wire to this tunnel. Error information will go to this tunnel. Yes.
We have connected one pin of potentiometer to the one of the analog pin of that Arduino, right?
Yes, sir.
So how our LabVIEW program know from which analog pin we have to take the input, because we have not mentioned anywhere.
We have given this analog channel, right, sir?
Analog channel, we are giving that Arduino analog pin number.
Yes, sir. So right now it is connected to 0. I can connect it to pin number 1 if you want, just for the sake of understanding. So I've now connected onto the pin 1. So I've connected to pin 1. I will make it pin 1 and run the program again. So I will see if I can rotate the potentiometer to get a different reading. Is that okay?
Yes, sir.
Yeah.
To
So
which analog pin we have connected that potentiometer to pin 1, right?
pin 1, sir. I'll just show you on the camera to which pin it is connected. I'll just switch on the camera. Not sure if you are able to see, but this is the analog pin. This one, this wire. This has gone to the pin 1, right? The first one I have left it, and it is connected to second channel, right? So the first channel is 0, the second is 1, then second, third, fourth, fifth. So 6 channels of ADCs. Now, if I remove it from this channel, it will take the floating voltage for the time being because it is not grounded. Let's say I move it to channel 0 back and stop the program and read from channel 0. Then you will get the proper voltage. Let it just run. You can see now 3.3 volts. Yeah, I'll rotate the pot and you can see the voltage increasing. Yeah. Okay.
So, sir, for channel 0 also and for channel 1 also, for both we are getting the voltage.
So while a channel is not grounded, when a channel is not grounded, it is typically will give you a floating voltage, right? So let's say my pot is set to 3.8 volts right now, right? And the analog port I am right now using is 0, right? So we are getting 3.8 volts. Now let me do it with channel 1. Nothing is connected to channel 1. You can see it will give us some floating voltage. It can be 0, it can be any other value. And that floating voltage will be available with any software you use. You can see it continuously reducing. So it's giving us a floating voltage. If I ground this channel, like I have some wires with me, I can possibly ground this. If I ground this channel, then I will see perfect 0 on that particular channel. So let me ground it. I have taken a ground wire and connect ground to channel 1. Can you see 0 now? What I've just done is I've given it ground because the channel is not channel when nothing is connected on the analog channel, it picks up the floating voltage. Floating point. Floating voltage can be anything. If you ground the channel, only then you can see 0 on that channel. Right?
Right. Thank you, sir.
Okay, I will stop the program for now. I will stop video as well so that it consumes less bandwidth. Now, is this program clear now? Now, we have been able to interface with Arduino. We've learned how to interface with Arduino. It's already 1:30. I think we should break for lunch.
Yeah, yes. That
Okay.
now the participants are very much interested. I can see that they don't want to even, they want to skip the lunch even. But we have to keep them healthy. We have next 3 days, 3.5 days.
So what we will do is, I think post lunch, I do not have any session. So I'll quickly lay out the agenda for tomorrow in that case. I think we have not been able to cover the Talking Tom application. So we'll have to include our Talking Tom application maybe tomorrow morning, wherein we will spend half an hour to 45
I have a
minutes talking.
question.
Yes, ma'am. Yes, ma'am.
जो बोल रही है ऑर्डिनो डिवाइस मैनेजर में दिखाया ना कि कॉम पोर्ट चूज कर
Yes, ma'am.
मैनर अगर हम डिवाइस मैनेजर में दिखाई दे रही है कि डिवाइस मैनेजर में कि हमने लगा रखा है बट वो LabVIEW में एज ए सेलेक्ट करने पे नहीं आ रहा तो कैसे उस प्रॉब्लम
So if it is, I mean, it's a serial.
Device manager.
Yeah, it is showing in device manager, ma'am. It is showing as a COM port. I mean, it's a serial device, or what kind of a device is
No,
that,
sir.
ma'am?
Network.
Network adapter. Okay. Now, in LabVIEW, how are you trying to access that network adapter, ma'am? Over what drivers? Because
Sir, we have
network.
for
Okay. Okay.
कम्युनिकेशन से हम उसको करते हैं वो ऐसे डिवाइस जो है अगर हमने करके रन कर रहे हैं तो वो चल रही है बट इन केस ऑफ LabVIEW इट इज शोइंग IMAX.
Okay. It's showing in Max. Okay. A network device will not show up in Max, ma'am. A network device will not show up in Max, ma'am, until unless it is from NI. If it is not,
but we can
your voice broke in between, but what you're saying is we can create a visa interface. Yes, you can create a visa interface, but on the visa interface, your communication protocol has to be well set. Second thing is on the device manager, while you right click on the device, you will have to possibly choose the proper driver for it, right? Right now, we're able to communicate over Arduino drivers directly with LabVIEW. For a network device, you may have to assign Visa as a standard driver for it if you want to access it in Max. If you want to access directly over, let's say, a TCP/IP packet or a UDP packet in LabVIEW, in that case, the device will not show up in Max, but you will still be able to communicate with the device. So to communicate with the device in TCP/IP or UDP mode, you can simply go to, let me search for the function TCP read, and I can take you to the palette. Yeah. What you could additionally do is, ma'am, give the details of the device on the chat window. Maybe I can look at the device and discuss that tomorrow during our session.
Oh, okay.
Right? Would you mind sharing the details on the chat window? I also have a question on chat window, sir. If Arduino already programmed, will it be able to interface? Not through links, Dinesh sir. If Arduino is already programmed with some other firmware, the only way to interface with LabVIEW would be just reading the serial commands which are being sent over serial.println command inside your Arduino. Did I answer your question, Dinesh sir? Okay, great. Okay, with that, we can break for lunch. So we'll meet tomorrow morning. We want to cover, we'll first of all look at few examples which you had to prepare, the calculator application, debugging tools. Then we will jump on to the audio application, the Talking Tom. Talking Tom is fairly simple to be built in LabVIEW. So we'll spend around half an hour on that and then jump on to machine vision and other tasks.
Sir,
I also want to cover, yeah.
Means there is no session 3, sir, today?
Yeah, it is there. It is there. That will be one expert lecture by Dr. Giraj Nyati.
Okay.
And on the topic Industry 4.0.
Oh, okay, okay, sir.
So that will be
Okay,
there. We'll meet at 2:30 for that.
Okay, sir. Yeah, I got it.
Okay.
So thank you so much. I can see the enthusiasm among all the participants. Yesterday also, we exceeded the time by half an hour. I think today it's same. We have exceeded by 1 hour. Then I don't know if this arithmetic progression will make it tomorrow is skipping lunch.
It will be there, sir, as the application is like that.
Yes.
Yes.
Thank you so much, all the participants. So we'll again come back and join us. That Dr. Giraj Nyati is the Chief Operating Officer of Genus Power Infrastructure will have his invited talk on Industry 4.0.
Sure, sir. Means tomorrow morning, Vinit sir will be in the first session. Am I right, sir?
First two sessions will be no. Vinit sir will be available from 11:30 a.m. onwards. Tomorrow morning, the first session will be on the cyber physical system by Dr. S. Akbar. He is the senior scientist from Siri Pilani.
Okay, okay, sir.
So morning 9:30 to 11 is his session, and then 11:30 onwards, Vinit sir will be available throughout the day.
Sure, sir. We'll meet again tomorrow, sir.
Today we'll meet that.
Yeah, I mean for Vinit sir, but yeah, there is another session, sir, at 2:30.
Okay. All
Means
right.
I was not wrapping up. I was just telling that. Thank you, sir.
Thank you.
Thank you. Thank you for your active participation. And in case if you have any feedback for me, please feel free to ping me separately on my WhatsApp number, or feel free to call me. I would want to incorporate that feedback in tomorrow's session.
Sir,
Thank you.
just one more thing.
Yes, sir.
Means how is the industry 4.0 means related to LabVIEW? Means that is what they are going to say, I think, right, sir?
They'll talk about Industry 4.0 concept in general, maybe not LabVIEW. LabVIEW can be used to build various Industry 4.0 systems, right? Like, let's say for Industry 4.0, you need to have cloud communication, you need to have connectivity between multiple machines over internet, and you also may want to have systems like condition monitoring systems for a complete plant. Those come under Industry 4.0, or rather Industrial Internet of Things application. Those can be built using LabVIEW, but in the interest of time, we'll not be able to cover it in these sessions as to how to do that. But once you build basic in LabVIEW, you can yourself look at various open resources available on ni.com to learn those topics. Like I can personally help you access LabVIEW and Amazon AWS connectivity, the Microsoft Cloud connectivity through LabVIEW.
We'll organize another Industry 4.0 using LabVIEW. The next.
Yeah, sure, sir. Means is it free, sir, as you said, for AWS and Microsoft connectivity to LabVIEW?
Evaluation for majority of tools is free, sir. I don't know whether the perpetual license is free. So that is something I'll have to check back. The evaluation definitely for almost all the softwares at NI is available for free for 45 days. I forgot to cover one topic which I had to cover, which is extending LabVIEW. The very first thing I'll do tomorrow morning is talk about extending LabVIEW.
Yes, sir. Means it is there right now for 45 days, right, sir?
It is right now at 7 days in majority of candidates PC. I will help them to extend it till 45 days.
Yeah, sure, sir.
Sure.
Okay. Thank you,
Okay.
Vinit. Thank you
you.
so much. So we'll again meet tomorrow. And if anyone is having any queries, they can reach out on the WhatsApp. They can contact Vinit also separately. He's very helpful. As you can see, he's answering to each and every query. And many of you have reached also him. I know that. So thank you, everyone.
Yes, thank you, sir.
Thank you. Thanks a lot.
Let us meet at 2:30 p.m. Bye.
Sure. Thank you. Have a great day ahead. Bye-bye.
Bye.
Bye, sir.
Bye.